before they come, we will just launch what we have done for the last week or 2 weeks before. Right? Can you all hear me? Can you all see the slides? Can you all see the slides? I think I have sent you the notes of this, right? Anusha? Do you have the notes of this lecture? Tanushan, I couldn't hear Tanushan.
Yes, sir.
Ah, you have the copy of this, right? Fine.
Yes, sir.
Right, good. Now,
Yes, sir. Yes, already uploaded LEMS.
uploaded. Okay. I forgot totally.
Yes, sir.
Good.
Yes.
So, mean separation. I think you better keep your statistical table. Hope everybody should have statistical.
So, yes, we have not.
No statistical table. Who is having statistical?
Yeah.
At the moment, who is having statistical table? Anyone? I need a help from those who are having a statistical table. Who is having a statistical table in your hand? Everybody has left at the hostel for Kuhan to study. Kuhan ta kudutittu vanditiyal pola. Canteen Kuhan padikkirathu. Yeah. Who is having at the moment? Who is having at the moment? Doesn't matter who is having at the moment. I need a help from the person who is having the table in your hand. Statistical table. Can send me a chat. And send through a chat who is having. I need a help quickly. Anyone having? You are having, right. Ganesh. Ganesh? Ganesh, I couldn't remember that. Ganeshamurthy. Miss Ganeshamurthy. Are you having the table? Yes or no? Ganeshamurthy.
Sir, I had.
You are having, right? Right. Can you WhatsApp some of the pages to all your colleagues, because we need look at this. Can you see this table? It's called Donut table. Do you see Ganeshamurthy? This table.
Yes, sir. Yes, sir. Yeah.
Yeah. The second table is this.
Yes, sir. I had.
Yeah. Take this table. Take the photograph of these two tables.
Yes, sir.
Take the photograph of Duncan and Donut table and send it to
Hello. Yes, sir.
WhatsApp la vote oda group la. Everybody can see that table. We need these two tables. And T table. T distribution table, student. T table and the third table is this.
Sir?
Third table is this, student.
Yes. Sir,
can you see?
Hello?
Can you see this table? Student table? தெரியுதா? 3 டேபிள், டனட் டேபிள் ஒன்று இருக்கு, டன்கன் டேபிள் ஒன்று இருக்கு, மற்றது ஸ்டூடெண்ட் டிஸ்ட்ரிபியூஷன், டி டிஸ்ட்ரிபியூஷன் ஒரு டேபிள் இருக்கு. இந்த 3 டேபிளையும் அனுப்பிவிடும். Is it clear to you?
Okay, sir.
Those 3 tables, put it into WhatsApp so that everybody can see.
Yes, T table.
T table also. T table.
Okay, sir. I will put.
Yeah. T table, Duncan table, and
sir,
3 table.
No, sir. No, sir. That video is not clear. இல்ல sir, தெரியல. என்ன
தெரியலையா? இப்ப தெரியுதான்னு பாருங்க.
Sorry, sir. Whatever.
இது Duncan table.
Yes, sir. Whatever. Sorry. Okay. Okay, sir.
Right. We will start with lectures. So we don't need the table immediately. So we will start the lectures from where we
Okay, sir.
last time. Hope everybody is, I'm not going to presentation mode. I'm simply applying it to the normal situation. Is it okay? Can you all see this? Right. We started with mean separation. Mean separation is done when we see a significance in the ANOVA table. In the ANOVA table, based on the F value that we have seen last week, based on the F calculated value, we say whether we reject or accept our null hypothesis. So suppose if we accept our null hypothesis, then no need of doing all these mean separation, right? If we accept our null hypothesis. What is our null hypothesis? No difference between means. That is our null hypothesis. Alternative hypothesis, at least one mean is different from the rest. So if you accept our null hypothesis, no need of doing our mean separation. On the other hand, if you accept your alternative hypothesis, at least one mean is different from the rest of the mean. So that you'll have to do the mean separation procedure to see which mean is different from the rest. I say different, it could be higher or it could be low, at least one. In that line, we have already spoke about few things. That is about the accepting null hypothesis mean, no difference between the means of three treatments, A, B, C. If you accept your alternative hypothesis, at least one of the mean. Here A is different from BC. Here C is different from AB. Here B is different from AC. Here all A, B, C are different. So we accept our alternative hypothesis, right? So this is the possible comparison if you have three treatment, A with B, A with C, and B with C. So three comparisons are possible. We talked about this comparison. Maximum possible comparison is K into K minus 1 divided by 2. So if you have 10 comparison, 10 treatment, 10 into 10 minus 1 divided by 2, which is 45, as we see last time. And when you talk about this multiple comparison, several comparison, we have come across a problem that is called as type 1 error problem. So type 1 error problem comes when you compare more than one pair of comparison. For that, we introduce two terms. One is CER, comparison-wise error rate. The other one is experiment-wise error rate. Two types of error rate. And we showed that experiment-wise error rate is more serious, right? Because suppose if you have 100 experiment, if you make one mistake in single experiment, it is counted as 1 out of 1. So suppose if you make one mistake in all experiments, all 100 experiments, 100 mistakes in 100 experiments. So that is the error rate. Experiment-wise error rate is 100%. But comparison-wise error rate, it is based on number of mistakes in the comparison. Suppose if you have 100 experiments, each experiments with 10 comparisons. All right. Each experiments with 5 treatments, so that 10 comparisons. So altogether we have 1,000 comparisons. So out of 1,000 comparisons, how many comparisons that make with mistakes? Suppose let's say if you have 100 mistakes, that is 100 divided by 1,000, which is 10%. So you see here, for a given situation, CER, the comparison-wise error rate is not that serious compared to experiment-wise error rate. However, this experiment-wise error rate is depend on the number of comparisons. So in other term, if you increase the number of comparisons, right? If you increase the number of comparison, definitely the experiment-wise error rate also increases. Therefore, we try to reduce the number of comparison as much as possible. So I'm going to talk about today, there are 4 or 5 types of comparisons available, how these comparisons can be applied to the real mean separation procedure. Right, I'm going to talk about the mean separation procedures. There are 4 types of mean separation procedures available. The 5th type we will learn a little later. It is a special one. So these 4 types are called as least significant difference, Duncan multiple range test, Donut test, and Turkey student-inized range test. So we are going to see all these tests one by one. First one, the least significant difference test. It is found by the person called as Fisher, Sir Fisher. He's a statistician called as father of modern statistics. Father of modern statistics. He lived in UK and did a lot of research on data analysis on agriculture aspects. One of the oldest and simplest method, and look at it very carefully, it is most widely misused as well when you compare multiple pairwise comparison. So you see here, sometimes it is also misused. People do it without knowing what we are doing. Because I have mentioned 4 different types of methods, each has uniqueness in terms of doing mean separation. So we cannot apply everything for everyone, every mean separation. So there are some reasons for different types of mean separation. Right. This least significant difference, I will call it as LSD, not the Latin square design. That is a different one. So this LSD is least square difference. It's based on the t-test, so t-table. In fact, it is the simple sequence of many t-tests. For example, in pool t-test, we talk about pair of comparison, 1 pair comparison in pool t-test. Similar to that, here we have structured the several t-test. Okay, we have structured several t-test. If you can remember the t-test, this is the x bar, for example, minus the hypothesis value or the mu value divided by standard error of estimate. So the standard error is s divided by square root of r. Okay, so this is coming from the first course, right? This t statistics, so we need to look at the t table, is distributed according to the distribution t distribution with r minus 1 degrees of freedom. The least significant difference test declare the difference between the means. Right, now how we declare the means difference, this t statistics we will have to calculate based on some value. Ultimately we call that this LSD value. We compare our LSD value. I will show you in a couple of seconds how this LSD could be calculated. What we are speaking about, if there is a difference between means of this is one treatment, this is the mean of another treatment. So mean of one treatment minus mean of another treatment. Have you seen this sign? How do you call this sign? Anyone? It's called as absolute value. What do you mean by absolute value? Anyone? What is absolute value? What is the absolute value of minus 5?
5.
5, good. So absolute value is 5 here. So here we are taking the absolute value, right? So that is why we have given that note. So what is the absolute value of 5? Again, that is 5. So you see, absolute value means it is considering only the value, not the sign. So if you look at the difference, the absolute value should be higher than LSD value to say that one of these treatment is higher than the other one. One of the treatment is higher than the other one. It's like our F calculated value greater than F table value and so on, right? So this is how we calculate the LSD value. It is depend on T alpha by 2, two-tail situation. The degree of freedom that we are using is error degree of freedom. So this is degree of freedom of error, or degree of freedom of mean square error. Mean square error mean it is the mean square error coming from the ANOVA table. Can you remember the error sums of square divided by error degrees of freedom, which is giving the error mean square. So here in this calculation, we are using error mean square into 1 over R1 plus 1 over R2. R1, R2 mean it is the replicate of this treatment. R2 mean it is the replicate of this treatment if the number of replicates are not equal, unequal replicate. As we said in complete randomized design, there is a possibility that they might have different replicate, right? In that case, we can use this formula. Otherwise, the rest of the thing is same, only this component is different. So that is 2 divided by R for equal R. If the replicates are same, then we can use this formula. Simple. The above statistics is called as studentized range statistics. The quantity under the square root is called as the standard error of the difference, right? Standard error of the difference. As an example, we can do a calculation as such. Look at this example, our complete randomized design. How many treatments we have? 7 treatments, right? 7 treatments, just a second. Can you all see the board? Right. Again, the same ANOVA, 7 treatment, 4 replicates. So here, equal replicates. So no problem with that. All treatments are having same number of replicates. So these are treatment sums of, source of variance, degrees of freedom, sums of square, mean square. This is the F value. Actually, F value is this. You shift the F here, right? Look at this error, degrees of freedom, total degrees of freedom. Total is 7 into 4 is 28 minus 1. Treatment degrees of freedom is 7 minus 1. So that 27 minus 6 is error degrees of freedom, which is 21. So there are sums of square already calculated, mean square is already calculated based on this degrees of freedom. F value is 9.83. So based on the table value, what we are doing, we said we are rejecting, let's say this, this is the F distribution. Let's say this is the value, some value. Don't worry about this value. We can look at the table, table value. Let's say this is 5.5. So this is the rejecting region. This is the calculated F value. So it is coming somewhere here. So we are rejecting our null hypothesis. We are rejecting our null hypothesis. Okay. So if you reject our null hypothesis, the next step is we'll have to go for a mean separation. So how we can do the mean separation, right? Now let's say how many treatments do we have? 7 treatment, A, B, C, D, E, F, G. Their mean values are such. Now we will have to calculate the LSD value. First step is we'll have to calculate the LSD value. So this is how we calculate the LSD value based on the formula. So this is the formula. T alpha by 2. Take the T table, alpha by 2. What is the degrees of freedom of mean square error? What is the degrees of freedom of mean square error? That is 21. So look at the value for 21. Everybody should have the table. What is the value? 2.08. So that is the table value. So this is from the table 2.08 into square root of, this is the mean square error from the previous slide. Mean square error from the previous slide. This is 2 divided by 4. 4 is the number of replicate, equal number of replicate in all cases. So we don't have problem. So we'll have to solve this. So once you solve, you will get a LSD value closer to 453. My LSD value is 453. Now what to do with this 453? Now we'll have to compare all the means one by one. Now I am ranking all the treatment means from the lower value to upper value. This is the lowest mean value, right? Low value to, so this is the lowest value. This is the highest value of the treatment mean. Treatment G, F, E, A, D, C, D. Right? How many treatments? 7 treatments. Okay? Right? So we have put them in ascending order, right? Lowest to highest. Now we want to compare one by one. So suppose, let's say I want to compare G versus F. I want to compare G versus F as an example. So we'll have to look at the difference. What is the difference between G and F? That is what we are going to look at it compared to our LSD value. Let's look at, we want to compare the third step, how this LSD value differs. Treatment F versus G. So we say, right, can you all hear now? Can you all hear now? Yeah? Can you all hear now? Is it clear?
Now, please.
Now clear. Maybe some.
Now, okay, sir. Clear.
Now, okay, sir.
Right. So now we have assigned all treatments into different order, right? Ascending order from lowest to highest, right? Now the second step is, let's say we want to compare F and G. Remember this, keep this F and G. I cannot show it both slides at the time. So think about F and G. What is the difference between these two treatments? So the difference between F and G, the treatment mean of F is 1681. Treatment mean of G is 1316. So the difference is 365. Compare this 365 with, right? Compare, because earlier we said the difference of let's say y1 minus y1 bar minus y2 bar, the absolute value, if it is greater than our LSD calculated value, if this absolute value is greater than LSD calculated value, then it is significant, right? That is what we said. Now, what is the y f bar and y g bar, the absolute value? Whether what is the difference? What is the value of this? This is 365, isn't it? The difference between this is 365. So this 365, is it higher than our LSD value? What is the LSD value? 453. Our LSD value is 453. The calculated LSD value is 453. Is it higher than our LSD value? So, if you look at our LSD value is less than, sorry, LSD value is higher than the calculated mean value. LSD value is higher than the calculated mean value. So, what is our conclusion? Is there a difference between these two treatment mean? Treatment mean of F and treatment mean of G. So, we found that there is no difference between these two treatment mean. Okay. So, in other term, we say it as NS. NS means not significant. Not significant. Not significant means the differences are not prominent. Differences are not prominent. So that is called as not significant. If it is significant, right? If it is significant, then we could say the differences are really prominent. Okay? Right. Now we will continue. Can you all see the screen? Can you all see the screen? So that is why here it is, yeah, it is given as not significant, because this 365 is not really higher than 453. It is smaller than 453. Right. Let's compare the second one, treatment E versus G. So you have the notes, right? E means next to G, sorry, next to F, right? Next to F, isn't it? So compare that, what you can say, the difference between the treatment E and the G, the value is 480. What can you say about this value? Is this value higher than our LSD value? Or is this value lower than our LSD value? So this is higher than this 480 is higher than our LSD value. 480 is higher than our LSD value. So we can put an asterisk here indicating it is significant. So we have put an asterisk saying that it is significant. Now, is it necessary for us to compare the remaining? For example, here we said right, we compared G and F and we said not significant. They don't have differences. We compared G and E. It is significant. Is there any necessity to compare G and A? We compared G and F, said no difference. We compared G and E, there's a difference. Now, my question is there a need of comparing G and A and G and D and G and C as well as G and B? Is there a necessity to compare G and A? If you compare G and A, again you will get the same results. Why? It will be significant. Why? Because already A is higher value than E. We have compared already G versus E, which showed a higher value, significant value. So that A is higher than E, D is higher than E, and so on. All these are higher than E. So that all will show significance with G. Do you get the point? Already, it is no need of comparison. So this is how we can reduce the number of comparison. Could you remember earlier we said that when you increase the number of comparison in any experiments, we intend to increase the type 1 error. So this type 1 error could be reduced using this concept. Okay? All right? So this is how we can stop further comparison with G. But we can compare with others. But comparing with G is not necessary. Since E is significantly greater than the treatment G, then the rest of the means greater than that of treatment E. Therefore, we need not to go further on comparison with G. So that there is no need of keeping comparing difference between means of treatment G and treatments with means greater than the means of E, treatment E. Right, for example, this is a SAS output. Let's see, I don't know whether I will do some exercise with SAS. We have, this is the SAS program. This is not necessary for this particular course, but I have included that also. These are SAS outcome. This is how the SAS output will give the results. This is the older version actually. This is how it is giving the SAS output gives the results. Look at the values or the results. So this is the important value. So this is what we call as LSD value. Computer calculate automatically for us LSD value, right? So this LSD value means with the same letters are not significantly different. You see, forget about this A because it is a continuation of A. You see here, treatment 4, variety 4, variety 2. So the treatment letters with the same letters are not significantly different. So is there any difference between 4 and 2? Because the same letters are coming. No different actually, according to this. The same letter mean no difference. So no difference between treatment 4 and 2. What about 4 and 1? What about 4 and 1? 4 is having A, 1 is having B. 4 is having A, 1 is having B. These characters are different. Here it is having A, here it is having B. So that it is different. There's a difference between 4 and 1. There's a difference between 4 and 3 as an example. You don't need to compare 4 and after 4 and 1, you don't need to compare 4 and 3. So this is how the output of a SAS comes. So every comparison is possible. For example, right now we can do a small study with a comparison. Look at this. Can you all see this? Can you all see this screen? Right. When you want to do a mean separation, I will first note it out that G F E A B C values are 1360, 1681, 1000, 96. Right, I'm going to skip this the screen. You can use your notes. Can you all see the board clearly? My LSD
Yes, sir.
yeah, my LSD value is 453. Now tell me, my LSD value is 413. Sorry, 453. We said there's what is the difference between these two? What is the value difference? This is 365. So that they both are same. So this is how you report it. So it is having an A, it is also having an A. Right? Because the letters which are having the same letter, the treatment which are having same letter are not different. So here it is having A, this is having A. What about here? If I put A here, we have seen the difference is 480. The difference is 480. Right? If the difference is 480, there's a difference between G and E. So that if I put the A here, so it is same as G, which is not true. For that, we can add another letter like this. Right? You have to train by yourself. So now you see, no difference between these two, but there's a difference between these two. There's a difference between, because here it has A, here it has only B. No A, here no B. Right, now, what about these two? Look at the difference. What is the value difference here? Somebody has to calculate. What is the value difference between these two? Let's look at the value difference between these two and these two. Tell me the value. The difference between these two. Calculate and see. What is the difference between these two and these two? Yeah. So the difference between these two is 446. Right? The difference between these two is
330.
331.
331. 31.
331, right? Okay. Now you see, no difference between these two. No difference between these two. What about these two? They are different. So we can say these also be no difference between these two. No difference between these two. That means here also it has B, here also it has B, here also it has B. No problem. Right? But what about this difference? This and this. It is more than 453. The difference between this is more than 453. So that we can leave it as it is. So this is how you look at the grading or the lettering. So this is also same. because only one is different. This is 127, this is 128, right? Okay. So what is the difference between these two? I will erase this, right? What is the difference between these two? Only one. Difference between these two? 332. The difference between these two? 447.
கவனிக்கிறானே
Hello?
காக்கிறானே உனக்கு ஒன்றும் விளங்குது இல்லை.
Hello? What is the problem? Hello? All right. So here also it is with the B. I will erase this. Right. Then what about these two? And these two, the difference, or these three? Calculate and see what is the difference between those. First one, 2552 minus 2128. 424. This is 425. This is 156. So it is a big one. So no difference between these two, but there's a difference. So you can say C. Right? The last one, 2, 6, 7, 8 minus 2552. This difference is 126. This difference 2, 6, 7, 8 minus 212 550. So definitely it has a difference. So no difference between these two. So you write it as. So this is how the lettering goes for this. It's a bit confusing, but sit and listen very carefully. Means with same letter are not significantly different. Means with same letters are not significantly different. Right? So this is how the final results comes. Look at the difference here. It is less than 450. So same letter. You have the letter D. Look at the difference here. It is more than 453. So the letter here cannot be the same letter here. So there is a difference in letter. So this is how you write down. Okay. Look at the past paper last year. There was a question on this. All right. Right. So this is how you write down your mean differences or significant differences. So this is an example, as I pointed out. You see, this is the outcome of one SAS program where we had 4 varieties. So each of these varieties, these treatments are actually varieties. Variety 4 is having higher treatment mean value. Variety 2, next one is variety 2. So these are replicates. Huh? Each of them are having same number of replicates, right? So these are 5 replicate for first treatment 4, 5 replicate for treatment 2. These are treatment. Huh? TRT means treatment. Treatment number 4, treatment number 2, treatment number 1, treatment number 3. So all of them having as the same replicate. Okay. So this is what we call as their respective treatment means, right? In a descending order. You can put it in either descending order or ascending order. These are the letters that we put it as. This is A, this is B, and C. So there's a difference between these two. There's a difference between these two, but there's no difference between these two. It's not significant, right? This is significant. This is significant, right? Okay. The final wording of this 4 varieties, variety 1, variety 2, variety 3, and variety 4, how these are differences can be explained like here. The yield from variety 2 and variety 4 are equal but larger than yield from all other varieties. So we have seen that the variety 2 and variety 4 had the similar, no difference in their yield, isn't it? Look at variety 4 and variety 3, sorry, variety 2, variety 4 and variety 2, no difference. Why? Both are having same letters. A, here also A. So that is why we said variety 2 and variety 4 are equal, but they are producing larger yield than the other rest of the variety. That is one thing. Second thing, the variety 1 yield is smaller than variety 2 and 4, but it is producing higher yield than variety 3. So that is variety 3 is the lowest yield producer. Variety 3 is the lowest yield producer. So you see in 3 sentences, we have summarized all this mean separation procedure. So we didn't compare all possible comparison. If you look at the drawback or the disadvantage of this LSD system, the only one critical value for all comparisons. So this LSD can be used because we calculated only one LSD value. Then we are comparing several means, pair of means. So that is one of the drawbacks. So only one value, we are comparing several pairs of observation. But later we will see one other method. In the other method, they have several different values for different comparison. We will see that, right? The second one is probability of declaring a false significant difference increases rapidly with number of comparison. So if you increase the number of comparison, definitely the false decision making will be increased, right? Therefore, it is recommended to have the smaller number of comparison. So the maximum possible comparison is t minus 1. The maximum possible comparison is t minus 1. Right? We'll have a break and continue. 10 minutes break and we will continue with that. Shall we start? So the second method, is called as Duncan multiple range. As I pointed out earlier in the LSD method, we have only one critical value. But in Duncan method, we have several critical value depend on number of treatments. Let's look at how this critical value can be calculated for Duncan multiple range test. This test was suggested to overcome the problem which has encountered in LSD, Here, if you want to have all possible comparison, we can use Duncan multiple range test. Sometimes it is also called as Duncan new multiple range test, DNMRT. DMRT is that if the two means compared are far apart, the critical value for the significant difference is large. So the same concept, if the treatment means are higher than the critical value, then we can come to a conclusion that there's a difference between those two treatments. Thereby, the probability of declaring the false significance is maintained at a fixed level of alpha, irrespective of number of comparisons. This is how we overcome the problem encountered in LSD. So the DMRT, when you compare two means, the critical value for the significant difference is large. So that is how we compensate for the type 1 error. This range, the DMRT, is depend on the range that we are talking about. How we can define that range? I will talk about this range in a few seconds. This range can take account of how far apart two means are compared is, right? So we have a different range value. How we calculate this range value, we will talk about it. The first step is you arrange the means according to the ascending or descending order, as we did it in LSD. Then we rank our means. You see, for example, if the treatment 1 mean is less compared to treatment 2 mean, compared to treatment 3 mean, compared to treatment 4 mean. So that means we are ranking them. This is the lowest, right? This is the highest. So we'll have to rank them. Now, after ranking, right? After doing the ranking, we want to see what is the range. Look at the range. For example, if I want to compare Y1 and Y2 mean, the rank is 2. So here, after ascending or descending order, here the rank is 2. Why? Because we are jumping 2 observations apart. Now, if I want to compare Y1 versus Y3, Y1 versus Y3, Y1 versus Y3, how many observations we are jumping? 1, 2, 3. So our rank is 3. So the range is 3. Right? If I want to compare Y1, Y3, the range is 3. If I want to compare Y1 and Y2, the range is 2. Suppose if I want to compare Y1 and Y4, what is the range? 1, 2, 3, 4. The range is 4. You see, if I want to compare Y1 and Y4, the range is. Suppose if I want to compare Y2 and Y3, what is the range? 2 range. Again, Y2 and Y3, the range. Similarly, Y2 and Y4, the range is 3. Right? Can you mute it? Somebody is unmuted. Mute it. Right. So when you compare Y3 and Y4, the range is 2. So here the range is 2. So when you have 4 treatment, the maximum range is 4, the minimum range is 2. I hope all of you understood how this range is produced. So this range is produced based on the highest to lowest value. Right, now we can calculate the the Duncan value. This is the Duncan value for a given range. So if you have 4 range, let's say 2, range 2, range 3, range 4. So we will have separate 3 values, 3 different values, right? How to look at these values, we will see. Take the Duncan table. There's a table called Duncan table, right? Not Duncan table, take the Duncan table. Let's say if my error degrees of freedom, as an example, error degrees of freedom is, let's say, 15. Error degrees of freedom is 15, as an example, just to show you error degrees of freedom, 15, right? Alpha is, let's say, 0.05. P is the range, as we talked about earlier. It can be 2, or it can be 3, can be 4, right? So it depends on number of treatments. Suppose if we have 4 treatments, so how to look at this P value? Look at this table value, the Duncan table value. There are 2 ways to look at it. One is row wise, the other one is column wise. The row wise is the P, the range. The column wise, it is the degrees of freedom of error, right? Now tell me, if the P is 2, if the P is 2, right? P is 2, what is the Duncan value? Degree of freedom is 15, error degrees of freedom is 15, as an example. What is the table value of this? If P is 2, what is the table value?
3.001.
Okay. P is 3. Oh, let's say P is 4. The table value varies. If the P is 4, table value is 3.25. What about this value? This value is same for any P values. This value doesn't change. Why? The mean square is a constant value. R is a constant value, so it doesn't change. Only this table value change. Since the table value change, this RP value change, right? So this is how you look at the table. So if the P value is there, so suppose if I have 5 treatment, let's say if I have 5 treatment, how many P values possible? How many range possible? P values, how many P values are possible? If I have 5 treatment, T1, T2, T3, T4, T5. P value is 2 is possible, 3 is possible, 4 is possible. What about 5? Is it possible? Yeah, because we have 5 treatment, T1, T2, T3, T4, T5. Right? So here, from here to here, it is 5. 1, 2, 3, 4, 5. From here to here, only 2 range. So the minimum range is 2, maximum range is 5. Right? So for each, you can find out the R value. So you'll have 1 R value for this comparison, 2nd R value for this comparison, 3rd R value, 4th R value. So 4 R values will be there. So depend on how you compare, this R value will change. This is from the table. Then if the difference exceeds the R values, because we have different R values now. So for each cases, we'll have to look at which jump it makes. Maybe 2 jumps, 3 jumps, 4 jumps. So based on this R value, we'll have to measure it. So this is the SAS program. This is the outcome of the, you see how many treatments are there or how many varieties are there in our case? 4 varieties, 1, 2, 3, 4. So if you, if you put them in ascending order, V3 is the smallest one, V1 is the next one, V2 is the next one, and V4 is the next one. So V4 is the highest value, V3 is the lowest value. Now you see here, from here to here, 4. When you compare 3 versus V3 versus V4, you have to use the RP value of 4th. If you compare V3 and V1, we'll have to use the, here the difference is, the jump or the range is 2. So we'll have to use the, this one, right? 1, 2, 3 values are there. Any questions? So when I compare V3 versus V1, I use this R value. When I compare V3 versus V2, I use this. Why? Because V3 versus V2, range is 3. 1, 2, 3. So I will use this one. When I compare V3 and V4, I will use that. When I compare V1 versus V4, which one I will use? When you compare V1 versus V4, when you compare V1 versus V4, which one do I choose? Second one?
3.
3, yes, because from V1 to V4, the range is 3. 1, 2, 3. So the range is 3. So we'll have to use the value of this for the comparison of those two means. So you see, not like LSD, here we have different values. So by that way, we are compensating for this type 1 error. Duncan test, the last one, or one before last. So this Duncan test is used for the comparison with control. In agriculture, we talk about control. For example, if you are doing a fertilizer trial, right? The department recommendation. So there is a department recommendation. So that is, we can consider it as control, right? Then we have another new mixture, fertilizer mixture F1, F2, F3. So I have 3. These are newly formulated mixtures, F1, F2, and F3. Newly formulated F1, F2, and F3. I'm going to compare with department recommendation because department recommendation is the one prevailing at the now where farmers are using. Now I want to check whether F1 is better than the department one, or F2 is better than department one, or F3 is better than department one. So what I say is, this is the control. The recommended by the department is the one which is controlled because we want to introduce the new fertilizer, whether these new fertilizer mixtures are doing better than the department recommendation. If they are better than the department recommendation only, I can release these varieties, these fertilizers. Is it clear? So always I compare with control. Not like earlier case. In early case, all possible comparisons are viable. All possible comparisons are viable. But now it is not like that. Let's say this is F0. This is the department recommendation. So I'm comparing with F0 versus F1. So to see whether F1 is better than F0. Second one, F2 versus F2. The third one, F0 versus F3. So only 3 comparisons are possible. I'm comparing with control. So here the control is F0, the department recommendation. F0 versus F1, F0 versus F2, F0 versus F3. Is it clear? So this is how we do the comparison. Okay. Right. Now we will go to the text further. The principle of Dannett test is the critical value is compared based on the number of treatment used in the experiment. When you look at the table, we want to exclude the control in the table. I will tell you how to look at the table. The critical value is given as D. So if, as usual earlier, if the treatment means are higher than the critical value, then we will say there's a difference between these two treatment means. So control versus the rest. So this is how we calculate, right? Take the table, Dannett table, take the Dannett table. This is same mean square error 2 divided by R. How to look at the Dannett table? Alpha is, as you all know, it is our alpha is 0.05. K is actually, it is the number of treatment minus control. Let's say in our example, we had F0 is the control. Then we had F1, F2, F3. How many treatment altogether? We have altogether 4 treatment. Now this K is actually excluding the control. If you excluding the control, in our example, what is the K value? Only these 3. Excluding the control. What is our K value in this example? Even though we have 4 treatment, 1 is control. So our K is here. Anyone? Not including the control. That means K is equal 4. Right? K is equal 4. Then as usual, the degrees of freedom is error degrees of freedom. Now let's say error degrees of freedom is 15 or 20. Now tell me what is the value. If K is 3, degrees of freedom is 20. If you look at the table, the row wise, you look at the K. The column wise, you look at the degrees of freedom. Take the Dannett table and get the value. K is, because our alpha is 0.05. In the Dannett table, you have for alpha 0.05 and 0.01. Right? Tell me for alpha 0.05, what is the Dannett value? For K is equal 3. K is from here, this direction, for 3. And for degrees of freedom, this direction. Tell me the value, anyone? Tell me the value. Anyone? 2.57. That is how you'll have to look at the table. Huh? 2.57. So that is for K is equal 3 and degrees of freedom 20 as an example. How this K comes? Excluding this control. Excluding control. Is it clear? Right. Now we will look at some of the calculation. So here we have only one critical value, right? Then if that critical value is smaller than the difference, then there's a significant between those two comparisons. So these are SAS program. If you do SAS, then in practical you might use it. So you see, this is the critical value, Dannett critical value, which is for this particular example. Dannett critical value for this particular example. So you see, can you tell me what is the control here? They have compared 4 versus 1, 2 versus 1, 3 versus 1. That's all the comparison is. Can you tell me what is control here in this case? Can you guess what is the control by looking at this?
1.
1. Exactly. Why? Because only 1 is compared all the time with the rest. So here 4 versus 1, 2 versus 1, and 3 versus 1. From the difference also you can understand. So which is higher? Which mean is higher? 4 minus the mean of fourth treatment minus mean of first treatment, which is having a positive value. The difference is positive value. So which is higher, 4 or 1? Treatment 4 or treatment 1? If this is a positive value. If this is a positive value, 4 minus 1, where you get the positive value. So what is higher? What is higher? 4 is higher, isn't it? Because 4 minus 1 is a positive value, so 4 is higher. 2 minus 1 is positive value, so 2 is higher. 3 minus 1 is negative value, so 1 is higher than 3. So this is the same example as we did earlier. So look at here, 4 versus 1. If you look at the 4 versus 1, this is significant. 4 versus 1, this is significant. 2 versus 1, that is also significant. So this is the indication of significance. And 3 versus 1, it is also significant. So all are difference. So actually here, 4 is better than 1, 2 is better than 1. What about this? Can we say 3 is better than 1? No, 1 is better than 3. So we can recommend 4 and 2, not 3 in this example. Because suppose let's say 1 is the standard one, compare 3 minus 1 is a negative value. So that means 3 is having lower value than 1. So we could recommend 4 and 2 because they are having positive value. We can't recommend 3 because 3 is having a lower yield than 1. So we cannot recommend with a standard one. So these two can be recommended. Right? So the yield of variety 2 and 4 are larger than the yield of from control variety 1. However, the yield from variety 3 is smaller than the control variety. So we can recommend 2 and 4, but not recommend 3. Right, the last test is called as Turkey studentized range test. Turkey studentized range test. Unfortunately, we don't have a table at the moment here. Don't worry about that. So here also the same concept as LSD. Here too, critical value is computed based on the number of treatments used in the experiment. Again, we have a table. If possible, I will show you the table next time. You see here, this is how the calculation takes place. This is the table value. Again, table value depend on number of degrees of freedom of error. Then we have the K value, number of treatments, and the alpha. The rest is same. Square root of mean square error divided by R. Right? So this is taken from the Turkey studentized table. If possible, I will show you next time. Otherwise, don't worry about it. Yeah. If mean differences exceeded H value, critical value, H, then two means are different. That is how we can interpret again the SAS program. Right? Again, the SAS program, how we can do the SAS program. Again, for the same example. So this is the Turkey critical value. So we look at whether the difference are higher than this critical value, right? by the critical value. Based on that, we say whether it is significant or not. Right? The interpretation is more or less same as the LSD, least significant difference. When you talk about selecting mean separation, if you have already planned comparisons, then we can use the LSD, least significant difference test. All right. And also, if you have smaller number of treatments, we can use LSD. If you want to compare all possible situation, all comparison, all treatment has to be compared, then we can use DMRT or TSRT, Turkey test. All right. If you want to do all possible comparison, you can do DMRT. If the comparisons of all the treatments against control done at test is most appropriate. So if you want to compare with control, then the Dana test is the most appropriate. Right. I have one more comparison, group comparison. I think this take a little more time than expected. So I think I will stop today at this point. We'll meet next week. Right? We'll meet next week to do the rest. I think by next week we would be able to complete it. Complete my section. Right. Any questions? Any questions? We'll have to go through the mean separation today. And if you have any doubt, we can discuss next time.